Alright, so this is going to be a video all about slope fields. Now what slope fields are, basically it's a representation of what the solutions of a differential equation could possibly be. So if you remember differential equations, they have that plus c when you're solving for them because you're doing the antiderivative, and you have that plus c. So that means there's infinitely many possible solutions for this. A slope field basically takes into account those infinitely many possible solutions and basically makes it's almost like an outline of what the solutions could look like. Slope fields are basically the opposite of what we were doing in Unit 2, where we were figuring out a point, or finding a point and then figuring out what the tangent line would look like at that point. So here I drew a tangent line, and then I have another point right here, and then I drew a tangent line that just grazes that one spot there, and then maybe I have one here. Slope fields are basically the opposite of this, in that instead of finding the tangent lines, you're given those little tangent lines, and then you're trying to create a graph based on those tangent lines that are given. Probably doesn't really make that much sense yet, so it's kind of good to see an example first. So we have this example right here. It says dy over dx is equal to x times y. Now this is a differential equation because it has the derivative in an equation, and if you notice, I have the slope field already made for this differential equation. And how it works is you can just pick any point. In this case, I just pick points that are whole numbers. So, and I'm basically sketching a little local linearization. So what would the tangent line look like at that spot based on the fact that this right here is the derivative. So if this is the derivative, you should be able to sketch a little tangent, a slope of a tangent, I should say, at any of these points. So let's take into account, let's just start at the origin, because that's probably the easiest one to look at first. The origin, the xy is 0, 0. So the coordinate, the xy coordinate for this is 0, 0. If you put 0, 0 into this equation, so 0 for x and 0 for y, you get 0. If you notice, the slope of this local linearization, this little line right here, is 0. Okay, you can do the same thing right here. The x is 0 here, but the y is 0. So if you put 0 in for x and then 1 in for y, well, 0 times 1 is 0. So if you notice it's 0 here, it's going to be 0 wherever the x is 0 for this example because it's x times y. If you notice, the same thing happens when the y is 0. All the slopes are 0. These all have 0 slopes. If you notice, there's no other 0 slopes anywhere on this. Okay, let's pick 1, 1. That's always a good one to do. 1 is x and 1 is y. If you notice, if you did 1, 1, that would be 1 times 1 based on this equation right here, which is 1. The slope of this point right here, slope at this point, this local linearization is 1. So you just kind of sketch off 1. I kind of look at the origin right here and then just make it 1 from there. Okay, let's look at 1, 2 right here. That would be 1 times 2. So the slope of this line right here should be 2. And if you notice, it is pretty much double of what this one is. And then this one, you can notice it's 3, and so on. So you basically do that for all the points that are here, and you end up with something like this. Now on a test, you're not going to be expected to draw this many. Usually you probably draw about like 6 or so. This is just kind of for an illustration purpose. Now you might be thinking, why do we do this? Well, this particular differential equation is actually easy to solve, and we're going to go over that in a bit, but there are some differential equations where you can't solve them the way we were solving them before. It takes a little bit higher level calculus to do that. So slope fields allow us to basically find the solution potentially of what it could look like, at least graphically. So you wouldn't actually be able to do it like we can with this one, but there are certain examples which we're going to look at where you can't do them. You can't solve the differential equation very easily. So I'm going to show you an example right here. So based on this problem right here, if you break it down right here, I separated the x and the y, so I divided the y on both sides here in the red, and then kept the x over here. I multiplied the dx over, did the antiderivative. This should all be a review. This whole part right here should all be a review from the previous unit for differential equations. If you notice, you end up with y equals a, which is that constant, kind of reinterpreted because it goes e to the c, e to the x squared over 2. Now, if you tried to graph this, you don't know what a is in this particular problem. You don't know what a is. So a could be anything. So you end up just graphing a bunch of these with a's different values. And if you notice, while you're graphing these, it fits along that slope field, which is the exact same slope field that we went over up here. But if you notice the graph, for these all follows it roughly follows the slope field. So it's like the slope field is almost telling you where the graph looks. You could have made these graphs without ever actually solving for any of this, just by kind of sketching an outline of where the graph is going. If you notice, it's 0 here, like we discussed before. It's 0 here for this one. It's 0. It's 0, and then it kind of follows along with what the slope field is kind of directing it to do. Okay, let's look at another example now. So this basically represents the slope field of the derivative being equal to cosine x. So that means if the derivative is equal to cosine x, then that means the antiderivative should be sine x plus c. And if you notice, it kind of follows what the sine x plus c graph would look like. Now, if you might not be able to see this very well, so what I'm going to do is actually graph some examples of potential solutions for that sine x plus c. Here's sine x plus 1, sine x plus 2, sine x minus 1, sine x plus 3, and so on. So if you notice, all these graphs basically follow what the slope field is doing to kind of show that it is the correct solution. Okay, let's look at another example now where you can't just solve it like we could solve this one, basically show the power of slope fields and how they're useful. All right, so now we're going to look at another example. This says the derivative is equal to x plus y. If you notice, you could easily make a slope field based on this equation, but you wouldn't actually be able to solve this equation using the techniques that we've learned so far in this class. But if you wanted, you could actually get an idea of what the solution could potentially be. So say that we were looking for the solution of this differential equation right here at 2, 0. So let's just color in this spot right here, 2, 0. So we know that the solution is going to go through that point right there. So for this particular example, I'm just saying that the solution is occurring at 2, 0. So that's why I'm coloring this in. Now, basically, I want a solution to this, and I have to follow the slope field. So the slope field basically guides me kind of in a general direction of what this graph is going to look like. So this is going to be kind of rough. This is not exact by any means, but you can kind of get the idea. I'm kind of just sketching this out in my head before I start. So it's going to look probably something like this. I'm just kind of being directed by the slope field, so it's going to look something like that maybe. Okay, again, not very exact, but at least we have some kind of solution that we can start to work with based on the slope fields. So that's basically the power of slope fields and what they're designed to do in case we can't figure out a solution very easily for a differential equation. We can use slope fields to kind of estimate what it could potentially look like. So if you have any questions about anything in this video, let me know.